Hello and welcome back to Physics for the 21st Century. Again, my name is Greg Perugini, and today's topic is ramp physics. So what do we mean by ramp physics? Well, it's just another example, like projectile motion, of 2D kinematics. We have, instead of like projectile motion, what we were doing before, we have motion down a ramp. Of course, we need to know the angle of the ramp that this object is coming down. Now, if we were coming straight down, of course, what's happening at that point, in a sense, you can look at this as a tilting of our axis. If we were coming straight down, it would only be under the influence, like free fall, of gravity, 9.8 meters per second squared. But if we're tilting it, the gravity dilutes the acceleration. Or I should say the angle dilutes the acceleration of gravity. Gravity is diluted as we come down this ramp. If we are opposed by friction, it really depends on the coefficient of kinetic friction between the two surfaces, the surface of the block touching the ramp. And the frictional force that's going to oppose it, in this case we're talking about a moving block, is that coefficient of friction times the normal. Now the normal, if I was on a flat surface, would be simply just opposing gravity. But that normal opposing gravity pulling down is diluted by the cosine of the angle. So where does this lead us? Well, take a look at this graph here. In a sense, it's saying more in detail what I was just talking about. The normal force being perpendicular to the surface is, if the surface was horizontal, would be just the force of gravity. But it's diluted by cosine of the angle. So I'm just going to draw that in. Make it clear. So the acceleration down the ramp is going to be equal to, I'll make this larger in a minute, the coefficient of kinetic friction times gravity times the cosine of the angle. That's going to oppose gravity coming down if this is a block sliding down. Gravity coming down, the acceleration due to gravity, this being friction, would be just simply g times sine of the angle. So as you see here, we have two opposing forces if this is coming down. The acceleration due to friction and the force of friction would oppose the force of gravity and the acceleration due to gravity down the ramp. Sometimes it's best, as I said before, to show this in an example. So let me make a larger screen so you can see that here. So I have this block. And let's say this is a 5-meter ramp. And this is a 25-degree angle. So look at that. what is the acceleration down the ramp? That's the question. Maybe time to the end of the ramp. Might be another question. Well, let's add velocity. What is the velocity at end of ramp? So let's answer those questions. What is the acceleration down the ramp? The acceleration down the ramp, 9.8 times sine of 25. The acceleration up the ramp would depend on my coefficient of friction. Let's give that here. The coefficient of kinetic friction is equal to 0.2, let's say. If there was no friction, it would just go down this ramp and it would just be the acceleration due to gravity, this number here. If you did that calculation, you'll get 4.1 meters per second squared. But let me continue on where I was. It is being opposed by 0.2 times 9.8 times the cosine of 25. That gives us 1.8 meters per second squared. So if you think it through, the answer, what is the acceleration down the ramp? Gravity is pulling it down. Friction is opposing it. What do you think the acceleration due to gravity is? 2.3 meters per second squared. Sounds pretty simple. So if we write down what we know, now we know the acceleration down the ramp is 2.3 meters per second squared. We do know the length of the ramp is being 5 meters. So if we were to figure out the time it takes to get to the bottom of the ramp, we already answered that question. Let's answer that question. And noting that we can say the velocity initial is 0, we're starting from the top of the ramp. We see here that we have enough to use the kinematic equation as written here. Change of distance is 5. Velocity initial 0, so we can just forget about that. Equals 1/2 times 2.3 t squared. This leads to what? T equals, let you do your calculation for a second. 2.1 seconds. So given that, what is the velocity at the end? Well, clearly, now that we have time, we can use that first kinematic equation that we had. But we can also use velocity final squared equal velocity initial squared plus 2a change in distance. Velocity initial, of course, is 0. This leads to velocity final squared equals 0 squared plus 2 times 2.3 times 5. 5 meters is the length. 2.3 is the acceleration. Solve for velocity final. The answer for that, 4.8 meters per second. So, look at this problem, analyze it carefully, and what you do see is that if this coefficient of friction was higher, let's say it was on rubber, something very, very sticky, the friction may be higher. The frictional force and the frictional acceleration may be higher. That doesn't mean it's going to go up the ramp, because the force of friction will oppose the motion, but only up to the force of that motion itself. It won't go over that. All you could say at that point is, based on if this was much higher, say at like 0.8, that at that angle, it wouldn't move. Let's take another example. Let's say I have a car going up a ramp. This is a totally different thought, right? Got a ramp here, and I have a car going up the ramp. Okay? Going up this ramp. And let's say the ramp is still 5 meters. Well, actually, I'm not going to even say that. Let's not say that just yet. It's going up the ramp at 5 meters per second. And it stalls. How far up the ramp does it go before stopping? If we talk about this being the same degree at 25 degrees that we had in the previous example, we still have our acceleration due to gravity equals 9.8 times sine, it's coming down this ramp, of the angle 25, just like we got in the last example, 4.1 meters per second squared. If we say the coefficient of friction is the same as before, the acceleration due to friction is equal to I'll write the coefficient first. 0.2 times 9.8 times cosine of 25. That leads us to, like we had before, 1.8 meters per second squared. But think about it. If there was no friction, would this car go up farther? Yes. Friction in this case is opposing the motion of the car going up the ramp. So the friction is opposing the car going up the ramp. And in that case, it's an additive effect. We're going up the ramp, not down. So if we were asked, for instance, how far up the ramp does it go, I can use velocity final squared equal velocity initial squared plus 2a change of x. The velocity final, when it reaches that final point, of course, velocity final is going to be equal to 0. 0 squared. Velocity initial squared, I said that, but let me write it in there, 5 meters per second. plus 2 times 5.9, the deceleration, negative, times the distance. If you do this math, you're going to get 2.1 meters. So, if this is going up at 5 meters per second, and it stalls, it's a 25-degree ramp, the coefficient of friction is 0.2. How far up the ramp does it go before stopping? The answer being 2.1 meters. Notice that we didn't have to know the mass. Doesn't matter. Okay, so in conclusion, since friction is an opposing force, it can go up to that opposing force, but not over it. If friction, based on the coefficient of friction, was high, it wouldn't allow it to go down the ramp. That doesn't mean it's going to jet up the ramp. It will go up to that opposing force. And as you saw in these examples, you still will need to use kinematics to figure out the net acceleration, to calculate velocity, displacement, or time down the ramp. Okay? Good luck.